Today we're going to talk about characteristic functions because there are a lot of applications in finance, especially in the areas where we use or assume normal distribution. And it doesn't typically work only for normal distribution. You can have any distribution and it will have a typical unique characteristic function. So first let's look at a typical structure of a characteristic function. This is how it looks, but we're gonna take a detour and understand what these terms actually mean. Let's say you have a random variable x and assume this is discrete, and then you have another scenario where you have a random variable but this is continuous, right? For a discrete random variable, what do we use as a probability distribution? You use PMF. You say if I know the values are sitting here, the probabilities sit on top of them, meaning the probability distribution in case of a PMF for random variable x correspond to the values themselves, so they sit on these particular points. This is why they are called mass functions, right? In a case where you say it's a continuous random variable, you use PDF, meaning since each and every individual points have a probability of 0. Why? Because you in case of, think what a continuous random variable means. Continuous random variable means any value in a number line, right? When you take events from a sample space and using the continuous random variable as a function, plot them in a real number line, you're saying any value on the real number line. There are infinite values in a real number line, so probability of being so precise is 0. What does it mean? You need to have a distribution. Let's say that the distribution looks something like this, just an assumption, right? Looks something like this. PDF says the probability for a given interval, let's say instead of minus infinity to plus infinity, you have a and b. For an interval a and b, the probability would be the mass function, the probability distribution function fx, and then you need a width. Why? Because this probability density function means for a value of x in this region, what the density looks like. Without an interval, you cannot really understand what the probability is. Think of it like this. Let's say you have a glass of jar and this is filled till here, right? Now I say what is the probability at this point, meaning what is the area at this particular point. You cannot say this, right? To say area in a glass of water, you need a width. If I give you a width, you can say, okay, for this width, this is the area, this is the corresponding area for this width. Similarly, this probability density functions give you a density around a point, but that's not enough information. You need a width to find the probability for that interval. Now similarly, in case it was discrete, your expectation for a discrete is basically summation of your individual values that you get and then their corresponding probabilities, right? In case you had a continuous, meaning a case of continuous random variable, your expectation turns into an integral, right? You have your corresponding x values and then you have your probability density function and then you have your width, right? This characteristic function we're talking about here, this is just a different representation of these probability distributions. How? Let's say what it truly means. This, if you guys are aware of Euler's identity, means this can be written as this, right? Now our characteristic function had expectation, so let's take expectation of this. So the entire thing would come under expectation. Now as expectations are additive, that means we can separate them. Right? Now observe what it means. This means for a random variable x, we are just averaging the cosine and sine waves. But because we have an imaginary number I, we have two separate curves. Now let's say the random variable was of continuous random variable types, meaning we had a structure of a curve. We had a curve, right? Whenever we say we are representing this probability distribution in terms of characteristic function, we mean that preserve all the characteristics of this continuous random variable and therefore the probability distribution, and create two waves. These two waves, one will have the cosine wave, the real part, the another one would be having imaginary part, the sine x. These two waves would contain all the information of the probability distribution. So you can think of this characteristic function as, you know, preserving all the qualities of this probability distribution, but in a wave-like form, if you can think that way. But why do we need to bother about finding a characteristic function for a probability distribution? So here what I want to say, the purpose of the video was to make sure that we understand how to derive the characteristic function for normal distribution, because there are a lot of applications in finance, one of which we can take an example of as, let's say I tell you that R1, R2, R3, these are daily log returns, right, of a stock, right? And then I say each of them are normally distributed. So R1 is normally distributed, R2 is normally distributed, R3 is normally distributed. Then I say, okay, since they are normally distributed, what is this probability distribution at R1 plus R2 plus R3? Meaning, you know, I want to find the total distribution after 3 days have occurred. In such scenarios, what you typically get is a convolutional integral problem. What is a convolutional integral problem? Well, we can derive and show it, but in short, it means you will have a scenario of double or triple integration. Because we have 3 days, you would be having a double integration problem. Why? Well, to understand that, we need to understand how does the probability density look for a normal distribution. For a normal distribution, the probability density fx looks like this. Why does it look like this? Well, we can have a separate video where we can discuss what are the corresponding characteristics for all of them, which ensures that you have a bell-shaped curve and then area under curve is 1. But let's say for now we understand that this is the corresponding probability density function, right? Now because whenever we say find a total probability distribution, for one of them you would have one integration, as you saw above, right? You have an integration here, right? So if you wanted to find a probability distribution for 3 days, you would be getting multiple integrals. Why? Because you have multiple days here, right? So solving a system where you have multiple integrals become really messy. This is where the characteristic function helps. Why? Because for a normal distribution, we have a clean characteristic function that can be stretched not only for 3 days, that can be stretched for n number of days, and such a representation of probability distribution would preserve all the characteristics of the original individual probability distributions, which are much easier to work because there's no integration there, right? So this is why I wanted to cover how to find a characteristic function for a normal distribution. So let us start. So what is our characteristic function? that we wrote above. It looks like this, right? Now, as we set expectation for knowing that this is a continuous random variable, it becomes this, right? Now we know what the probability density function is for a normal distribution, but instead of x we also have this, so we're gonna replace x with this, and we're gonna replace fx with this. So instead of x you have e to the power I ux, instead of fx you have the probability density function that looks like this. And then you have your width. We need to solve this, and by solving this we'll be finding the corresponding characteristic function. So let's solve this. This is a constant, it will be pulled out. Then you have iux. Now you have two a's, right? Let's use the property of e to the power a plus e to the power b into e to the power b e to the power a plus b. So this becomes this dx. Our job should be to simplify this region. Why? It has a lot of components of x mixing with I, u, mu, sigma. When we have a width of dx and we're integrating with respect to dx, so it makes sense to simplify this, right? So let's focus on simplifying this region. Expand this. Divide by 2 sigma square, each of the component becomes rearrange them like this. You have 2x components, take them common, it becomes iu plus mu by sigma square minus mu by 2 sigma square. Take this as a common denominator. Push that sigma square inside, it becomes I u sigma square plus mu minus mu square by 2 sigma square. Take that x outside, sorry, take this minus outside, it becomes this. Now this right here, this, what does it look like? This looks like x square minus 2x into something, meaning x square minus 2x, let's say this is a. We add a square to it and subtract a square. What does it become? X minus a square minus a square. We need to represent this way. Why? Because this x gets cornered inside a whole square, and that will really help us because it is not getting convoluted to anything else. Now let's try to use this to structure this entire thing this way. So this becomes x minus the a would be I u sigma square plus mu square minus this a square divided by 2 sigma square minus mu square by 2 sigma square. Now we have this. we're taking it out, and plus we're gonna expand this square. This becomes I square u square sigma to the power 4 2I u sigma square mu plus mu square by 2 sigma square minus mu square by 2 sigma square. This I square is imaginary root minus 1, so squaring it becomes minus 1, right? So if we were to divide each component by 2 sigma square, this becomes u square sigma square by 2. So okay, yeah, plus, so yeah, so plus 2 gets cancelled, sigma square gets cancelled, you have iu, then you have mu sigma square by 2 sigma square minus mu square by 2 sigma square. This gets cancelled, then you have sigma square mu square by 2 sigma square iu minus u square sigma square by 2. I think we have simplified enough. We can use this in our original value that we have. We wanted to simplify this. Let's go back there. So original, we had 1 by sigma root 2 pi minus infinity to plus infinity, and then inside integral we will have x minus I u sigma square plus mu 2 sigma square. This is plus, so you can divide it and write like this. Similar principle of e to the power a into e to the power b is equal to e to the power a plus b. Then you have dx. Now if you see, these are all constant, meaning this can be pulled out of the integral. So this becomes 2 pi I u square sigma square 2 integral of this. Now there's a whole derivation for Gaussian integral. We can cover this as a next future video, but to solve a Gaussian integral, basically you need to assume this is I, then you need to square it. You will have double integration. So to solve the double integration, you need to change the dx dy to polar coordinates. So there's a lot of stuff, but this basically simplifies to sigma root 2 pi. We can have a future video where we can prove that the solving the Gaussian integral simplifies to sigma root 2 pi, because we need to do so much, because there's no simple antiderivative for Gaussian integration. So we need to do some manipulation, right? But let's say we understand that this simplifies to sigma root 2 pi. This whole thing becomes u square sigma square 2 into root 2 pi, meaning this gets cancelled. So you are left with this, right? Now observe something. This characteristic function that we get when we solve the probability distribution, assuming it's a normal distribution, well, it preserves both the mean and the standard deviation. This would be mean, the mean and the standard deviation, right? So what does it mean? This means that the typical characteristic function that we get for whatever normal distribution had as a characteristic of mean and standard deviation, this would be preserved but in a wave form, just like we had discussed before. Why does it help? Well, in our previous example, we had R1, R2, R3, blah 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 blah. Just like we had discussed, to avoid convolutional integral structure, we can simply use this, and this can get multiplied or scaled based on any number of days that you need. Let's say you need for R4, R5. What does it mean? You just take this characteristic function and you scale it, right? You scale this characteristic function for n days, right? So whatever you have, you just do to the power n. You have for n number of days the corresponding characteristic function. It helps. Why? Because you do not have any integration to worry about. So this characteristic function becomes a really simple way to represent the same underlying normal distribution, which makes our job really easy. In future, I'm gonna make videos covering where it falls in terms of GBM, or there are a lot of models like Histon and jump diffusion model, which kind of use this particular logic but in different ways. We're gonna cover those videos in future, but the primary purpose of the video was to show how solving the normal distribution using the characteristic function form, this expectation form, we can derive a simplified structure of the same probability distribution but in a wave-like form. So that was the purpose of the video. Thank you.